Let's go back to building the model again. We'll select the same dataset. This time we are going to define a cost. Look at this. The cost is a negative number. It indicates how much weightage you give to an incorrect prediction. So currently both are set to 1. That is, predicting benign as malignant and malignant as benign both are treated the same. But we want to penalize the model when the malignant is diagnosed as benign. So we'll give an additional cost for this case. So let me make this as -3. Okay, click on next. Next again. We'll be executing only the decision tree algorithm as we did last time. Next again. Okay, the model has run. We'll go to the last tab. Okay, look at this. The model has got 94.62% of the overall predictions right. If you remember, this is exactly the same number which we got last time. The accuracy last time when we had both the cost as -1 was also 94.62%. Even now it is 94.62%. But here comes the difference. The precision here is 90.38 and recall 95.92%. Okay, so the precision last time was 92% if you remember, and recall was 93.8%. So our precision has come down while our recall has gone up. So this is what we want. If you remember, if you go back to the last video where I have explained the precision recall trade-off. So for this particular problem statement, we are okay with a lower precision, but we need as high a recall as possible. So that has been satisfied now by choosing the cost as -3 for whenever the model predicts malignant as benign. So what we'll do is we'll go to our old test data set which we used last time, and we'll execute this model, or we'll make our predictions using this model on the test data set, and then we'll compare the results. Apply model, apply a new data set. The same, add data, the test data set. Calculate predictions. Yeah, we'll export this into an Excel sheet. Okay, so this is our prediction for the test data set. After adding the cost parameter, let us create a confusion matrix as before by using a pivot table. Diagnosis to rows, prediction to columns, count of some value. I'll rename this as actual and predicted. Okay, if you look here, the model has made 7 mistakes now. 4 times it has predicted malignant as benign. 3 times it has predicted benign as malignant. Okay, if you remember the earlier case, here we had the cost as -1 for both incorrect predictions. I have this result with me. This is the earlier result. So even here, the model has made 7 incorrect predictions. But the difference being, it has predicted malignant as benign 6 times. Now it has predicted malignant as benign 4 times. So there has been a reduction in the number of times the model has incorrectly predicted malignant as benign. So this has occurred, or this has happened because we are given the cost parameters -3. But it has come at a cost. So earlier the model made only one incorrect prediction in terms of benign being predicted as malignant. It has gone up to 3 times now. We have successfully reduced the number of times the model makes an error in predicting a malignant case, though it has come at the cost of increasing the model error in predicting a benign case. You could try out a couple of values for cost, -4, -5, etc., and take a look at the predictions. If our intention is to eliminate the incorrect prediction of malignant completely, we may need to set a high cost for the incorrect prediction of malignant. This will of course result in a higher number of errors in prediction of benign. which we may be willing to accept. For other classification problems, it will be up to you to use your judgment and business knowledge to determine the optimal cost parameter to be set. That is, how much false negatives I can accept in order to get a higher number of true positives. Okay, fine. In the next video, we'll use random forest to do the same classification.